Good evening, everyone. I'm Shafali Agarwal, a PMRF scholar in IIT Madras, and today is our fourth TA session on the topic design of steel structure. So, in this fourth week, you might have studied about the eccentric connections. Like last week, we have studied eccentric connection where was lying in plane to the connection. Here we will study about load, which is like perpendicular to the plane of connection. So same way we will study about the bolted joints and then welded joints. And next thing which we will be studying this week will be the introduction to the design of tension members. So at this point, our connections will be over, and then we will start the design of our tension members. So first, we will see the eccentric loading in our bolted joint. So this figure we have studied last week, where our load is being applied in the plane of the connection. So if we see our connection is in this direction, and load is also applied in the same direction. But now we will study when load is applied perpendicular to the bolts. So our bolts are applied in. So if we see our bolts are in this direction and our load is applied perpendicular to this direction. So this is our bolt direction and our load is in perpendicular direction. Here, this was our plane. This was the, this is the plane and the load was applied in the same direction as the joints, bolts. Here our load will be applied perpendicular to the direction of our bolts. So when a case like this happens, same way as we have seen in the direction of a direct load will be applied, and because of this eccentricity, there will be a movement in our plate or in our connection. So a movement will be there. So uh, same way we will say the bolts are in shear and tension. So both type of loading will be there. So first thing is there the neutral axis. So in the case of our bolted joints, when a load is applied in the perpendicular direction, our uh, a neutral axis will be not be in the center, right? It will be at some point h by 7 from the base. Why this is the case? Because of the cross sectional area. So mostly the cross sectional area of the bottom bolts will be higher than that of the upper bolts. So because of that, the masses and the cross sectional area will change our neutral axis to this point. Here we are assuming that our neutral axis is lying at h by 7 from the base, from the bottom edge of our bracket. Okay. So if we go for the design of our, if we go for the different forces that is applied to our bracket due to the centric bolts. So first thing is due to the shear force. So because of the shear force, a direct load is applied P, and for the because of the tensile force, how we are calculating? First thing is tensile force we are calculating. Our tensile force will be proportional to the y. What is y? Y is distance from neutral axis to the selected bolt line. So if we are selecting this bolt line, so this would be our y. If we are selecting this bolt line, our y would be changing same way. So we have to find the critical y also. So t is proportional to y. So changing the proportionality, we are having a constant k. So tensile force T is equal to k into y. And from there, we can have the proportionality constant as T divided by y. Next thing is, because of this tensile force, a moment is acting, right? We have seen moment is equal to P into E normally in our previous cases. So here, because of this tensile force, the moment is there. So that moment will be load in T into yi. So yi will be the critical y distance. So T is given by ky. So the moment will be kyi square. So this is actually square. So calculating the total moment. Total moment will be given by summation of different ky square. Okay, so as y will be changing, our ky square value will be changing. So that would be our total moment. So if we apply k we have calculated as ti upon yi. So from there we can get our moment value is equal to ti sigma yi square divided by yi. And changing the directions, we can get the tensile force as movement into yi divided by summation of yi square. So if we see the at the equilibrium at the neutral axis, our total tensile will be equal to the total compressive force. So if we calculate the compressive force, this compressive force at what point it will be acting. So this was our figure. Okay, this was our tension part and this was our compression part. So to calculate the moment, if we have to calculate the moment about neutral axis, we are calculating moment due to tensile force. This is this one plus movement due to compressive force. So compressive force is compressive load into distance y dash. So distance y dash will be this distance, and this distance is 2/3. If we see this triangle, this is a right angle triangle, and our center will be lying at the 2/3 from this point, right? Our CG will be at 2/3 of this point. So 2/3 of h by 7. So that will be our y bar value. That is coming as 2h by 21. Okay. So m is equal to m dash plus cy bar. So calculating this thing, we can get our total moment, that will be m dash bracket 1 plus sigma yi divided by yi square into this distance 2h by 21. So this movement can be calculated. We will shift to the values, and this movement will be uh, can be calculated as this is our total movement due to tension m dash. This can be calculated as this formula. Okay. Next is how we can design these type of bolted joint, eccentric bolted joint when load is perpendicular. So first thing is we will select any nominal diameter of our bolt. Either it will be given to us or we can select based on the different criteria like as in code we have given if it is shopware, uh, different conditions are given. Based on that, we can calculate our nominal diameter of bolt, and we are assuming our pitch and edge distance suitably for the same diameter of bolt. Then we will calculate our shear strength. So all these design steps we have already done when we were doing design of bolts. So same thing we will be following here. We will calculate it in our shear strength, and then we will select the number of bolt lines and external moment due to eccentricity. So based on this, we can calculate a number of bolts. So mostly these terms, either you have to assume these values or these will be given to you in the question. At least something will be given to you in the question. So from these values, you can calculate number of bolts per line, right? 6m divided by n dash into p into vsdv. So n is the number of bolt lines, p is our pitch, v is our shear strength, and m is our moment. So from there, you can calculate number of bolts in one line. Then from this value, from number of bolts, you will calculate the shear force. This is exactly the same design which you have seen in the normal design of bolt. So same procedure we are following till here, actually till here. So we will design shear force, tensile strength, and then tensile force at the extreme critical bolt. So this is the value which we are getting here, tensile force kyi. So yi is our extreme bolt distance. So this we will calculate. So then we will apply the check. So our check should be the calculated design strength should be less than the calculating strength should be less than the design strength. Same way calculated tensile strength should be less than the calculated design strength. So from this last point is we have to check it again, shear and tension using interaction formula. So this is our interaction formula. So if this interaction formula is followed, that means our design is correct. If this is not followed, then we will increase our diameter or decrease our diameter, and same procedure we will follow again. So this was the eccentric bolt joint, and next is the welded connection. So same way we will see if we have fillet weld or butt weld. So two type of welds are there. You remember fillet and butt weld, no? The two plates are connected in this way, then it is a fillet weld. And in case of butt weld, two plates are connected end to end, filled with. So for both the cases, we will see the design how this eccentric load will affect our design. So first thing, the same way that as we have seen it, our bolts, it will be affected by shear stress as well as tensile stress. So shear stress will be given by load divided by effective welding. So all these values we have already calculated in our previous lectures. You can see it from there. Next is the first thing will come to the fillet weld. So the total length of our fillet weld, it is called as D, effective depth. So first thing is shear stress. Shear stress is load upon area. So in this case, area will be effective length and throat thickness, right? So effective length in case of fillet weld will be given by 2D, as you can see. 2. So 2D will give us the effective length, and TT is the throat thickness that we are calculating from the size of it, right? Next is the stress due to bending. So stress due to bending, we have seen the formula m upon sigma upon y is equal to m upon I. Here you can see it is a simple rectangular section, so I will be uh, PT cube by 12. Since two in two sides it's there, so we are multiplying by 2, and y is equal to distance from neutral axis, sorry, it will be d by 2. So that's from there we can calculate fb will be given by m is p into e, and then putting all the values here, we are getting fb is equal to 3pe divided by dt d square. Okay. Last is the effective stress. So effective stress in case of fillet weld will be given by under square q square plus fb square. Q square plus fb square. And this should be less than equal to weld strength, which is given by fu divided by under root 3 gamma. Okay. So when we have to design this type of weld design, what we are doing, first step is we'll calculate our throat thickness, select our size of weld, calculate throat thickness and weld strength. Weld strength is given by Fu divided by under root 3 gamma mw, this way. Okay. Next is the, we will calculate this depth of our weld. So this depth of our weld is given by the formula 3pe divided by dt rw. Okay, this is the standard formula. So using this formula, we can calculate the depth of well. And next step is increase the depth to certain percentage to accommodate shear stresses here. So we will assuming it is coming by 7.3 mm. So we will approximately take it as 20 or 25 mm, so that like to round it off to so that our shear stresses are also accommodated instead of doing our instead of repeating our test again and again, we will increase our depth a little bit. Next is that we will calculate shear stress. So shear stress again will be given by load upon area. Area in this case is 2d into t, throat thickness. Okay. And next is the calculating stresses due to bending. So bending stresses is, I think it's wrong. Its formula is wrong. I will see this. So we will calculate the stresses due to bending. And last is the equilibrium stress, which is given by QE square plus FV square. Wait, just give me 5 minutes. I will check the values. Okay. So stresses due to bending, we can calculate in the same way as we have calculated in this case. Here we have calculated now stresses due to bending m upon I into y, which was coming as 3pe td d square. So this value will be 3pe te into d square. Okay. And our equivalent stress will be given by under root q square plus fv square. Okay. So if our equivalent stress, that is the final step, if our equivalent stress is coming more than Rw, more than the weld strength, then we have to design it again. We have to change the size of weld again, change its hot thickness, and design our complete procedure again. If not, then our design is fine. Next is the in case of butt.
Ma'am, I do have a small doubt there.
Yeah.
Yeah, if you, can you go to the previous slide? Okay, here we have a step where we are calculating depth of the weld.
Yeah.
I mean, why we are having that step? Because if it was like it will depend upon the size which will attach. If the length is more, we will increase it, and we should, with respect to that, we should find the size of the weld, I guess. Because if not, if D is like, let's say in this situation, we can decrease the D. In
Yeah.
the, let's say, if it is decreased and we got like 3/4 of the D, and we will be welding from the, if we weld it from the top 3/4 of the, then the I value will be different for this situation.
I didn't get your question.
I mean, okay, we are calculating FB value with respect to FB, like mean bending stress,
Yeah.
movement by I into Y. Here we are calculating I. I mean the I value and Y value is considered when whatever we are considering is respect to where D is like completely from top to bottom.
Yeah, we are considering so.
So if we change the D value, like if the D is not like completely D or 3/4 of the D, then this I and Y values will be different, right? Because the center of gravity will be different for that.
Yeah.
So those values will be different.
This value will be different, even our shear stress will be
Huh.
changed.
Yes, I think D should be like constant, like where depending upon the size of the member which is going to be attached, and with respect to that, we should play an like the S value, like uh, size of the wheel L, like what we're doing in the previous one in the fillet joint.
So, see, these are just the design steps which are given to us according to the code. So it will depend on our
Achha.
questions. Most of the time D will be given to us.
Okay.
So
Okay,
it's
ma'am.
just the design steps which are actually given in the code. It's not like we will follow the same steps every time. I feel most of the question D will be given to you. If not, then you can calculate D.
Okay.
But I still couldn't understand
But
your.
like if I mean, even though I think if let's say in this problem where I was asking the question, like if it is like 3/4 of D,
Hmm.
so if, will it be justified if the 3/4 of the D from the center, like from the center, the both the sides are same, like what you, I mean, whatever the 3/4 of the D is like placed from the center, center to top. I mean, from the center now we are having D by 2 and D by 2, no?
Yeah,
D by 2 to top, D by 2 is the bottom.
you're telling y is d by 2.
Huh.
Hmm.
Yes. Now, if we got 3/4 of the D, like let's say now
Now
3/4 of
d
the D,
is
we
this much. If d is this
huh,
much, then
huh. Now since we will getting the I value and Y value different, so can we place that 3/4 of the D so that half of the 3/4 of the D is equal to the whatever Y by 2 is there.
yeah, it will be same. Like if
Then
I,
we can it can
it will
it,
vary according to our d value. If our d
okay.
value is 3/4 of d,
Hmm.
then our t value will be, sorry, uh, t value will be 3/4 or 3 by 8 of d, right?
Oh, okay.
Case, so not t value, sorry, y value.
Y value.
Y value will be 3 by 8 of d. So same way, this FB value will be changing.
If that's what I meant. Like for compensating that,
Hmm.
if we place half of the 3/4 of the D, like 3/8 D value top. I mean, from the let. Sorry, ma'am, I was little not able to express. Okay, can you draw a line from center line, like where D is represented? From that, draw a small line to top and not from there. The middle line where you are drawn already. From that, draw a small line. Okay, man. Same thing. Other small line to the bottom. Huh. Now let's say the top line measures of 3/8 of the D.
This much is 3/8 of the d.
3/8 of the D, and the bottom is 3/8 of the D.
Oh,
Now if we take like this, like where we are getting D value as 3/4 of the D, if we weld in this way, like 3/8 of the D on top and the bottom, do we get the values where FB is, where we are calculating FB, Y value as D by 2 only?
yeah, because this is what we say symmetric, no?
Hmm.
See,
Huh.
if it's symmetric, then our y will be always equal to d by 2. No
Huh.
matter whatever our d value is.
Okay. So
See,
that
in
can be
this
done.
case, if our fillet
Hmm.
weld was in this shape, imagine,
Oh,
then you can't
okay.
say your t is d by 2. Then you have to calculate your t value, your
Yes, ma'am.
center of gravity, sorry, CG point.
Yes, yes. Huh.
In that case, your y will change. But if it is a symmetric thing, irrespective of your d value, then your y will
Hmm.
always be d value.
Okay. And why we are calculating it d by 2, ma'am? The bending stress value.
Why we are calculating y value?
I mean, why we are calculating, why we are considering y as d by 2 while calculating the bending stress.
Because y value, this formula you might have studied, no? Moment of inertia formula.
Yes. Huh.
In this case, y will be our distance from neutral axis.
Huh. Yes. But we are considering at the center. I mean,
Because it is symmetric. That's why we are considering it. So
acha.
it
Okay.
just depend on your say geometry of your object. So
Mm-hmm.
the way your geometry will change, same way your y will change.
Okay, we have to calculate to the extreme to the center of the center of the
From
weld.
CG point to the
CG
edge.
point. Okay. Okay, ma'am. Got it.
So same way when we do for the butt weld or groove weld, in this case our D value will be changes since we are welding it completely. That complete weld will be there. So D will be the single D instead of two D. There our fillet weld was in this shape. So our D was 2D. Here D will be single D. So same way everything will be changing. FB will go to 6PE by DED square because that 2 will be cancelled out. So it will come 6. We can use the same formula and calculate it. And equivalent strength will be given by under root TQ square plus FB square. So this formula I think we have already studied before. So same way we will follow the design of buttress. Okay. So this is about the eccentric loading when our plane is perpendicular to the uh, connection. So these are the different design steps. Question we will see at the last. If anyone have any doubt, you can ask now. Okay. If no doubts are there, then we'll go to the next topic. Next is the tension member. So these are the type of members in the steel structure which are subjected to the axial tensile forces. So some of the example of our tension members are truss members, like you might have seen in bridges. These type of trusses will be there, or cables in suspension bridge. These are suspension bridge. You will have some cables. So axial tensile force will be there on our cables. So that's why they are called as tension member and or the bracing of our building. So if braces are applied, we are also called as the tension members. So in case of our tension member, mostly our cross-sectional configuration will determine the strength of our, just give me one minute. Sorry for the distraction. So in case of tension member, the strength will mostly depend on the cross-sectional area of our uh, element. So mostly in tension member, what we are using circular rods or angle section. These are the most commonly used tension members in our steel structure. So when we come for the strength of our tension member, what are the different things which are affecting our strength is main thing we are telling at the cross sectional area. So how first thing is bolt holes. So because of bolt holes in our section, there will be a reduction of net area. So because of the decrease in net area, there will be a decrease in strength value. Next is the geometry factor. So if our G by D value is low, G is our gauge length. We have seen in our bolts now, gauge length, and D is the diameter of our bolt. So if G by D ratio is low, there means there is less, there is a contraction in net area. So if there is a contraction in net area, then that it means the strength will be more. Okay, this is the ductility factor. So if our material is more ductile, then we will have even distribution of stresses, which will increase our strength value. Next is the effect of residual stresses. So residual stresses is mostly in case of fatigue. Fatigue means continuous loading one after another. If we have a fatigue continuous loading, we will have more residual stresses, which will decrease the our strength of our element. Next is the spacing of fasteners. So if our fastener are spaced very closely, they will block the shear failure at the ends. So last is the shear lag effect. So what is shear lag? Shear lag is the non-uniform stress distribution in any member in which each element of the cross section is not directly connected, right? This is our member. This is our L section. Our connection is provided here. So because of this, our in this element there will be a non-uniform stress distribution, right? Because this connection is not at the center and it's not connecting our complete element. So because of this uneven stress distribution, there will be a shear lag, uh, especially in this element. So that is the shear lag. Because of this shear lag, our strength of the complete element will be decreasing because our complete cross-sectional area is not effective at the critical section. So if we say this is our L section and this is our CG point, uh, this is our CG point because of our connection. Our CG point will change from the center point. So at our effective cross-sectional area, complete uh, critical section is not involved. So because of that, there will be a shear lag. The stresses won't be evenly distributed. So because of that, the strength of our complete connection will be, strength of our member will decrease. So the first thing is we have to calculate the next sectional area in case of tension member. So first thing we will see in case of plate only. In this week we have done only plates. So two type of plate section we are checking. First is chain bolts or staggered bolts. So chain bolts means all the bolts are lying in the same sections one after the, and staggered is they are not lying in the, like this is the chain. If you see column and rows, there is a symmetry. But in case of staggered bolt, it's like a zigzag position. So in case of chain bolt, our net area is given by B minus LDH into T. So total width minus uh, number of number of bolts in one line, like in this case 3 into diameter. So total width minus these three widths, right? So these three widths are given by N into D. So total width minus these three width will give us effective width multiplied by thickness, throat thickness, multiplied by thickness of our, sorry, not throat thickness, thickness of our plates will give us effective net area. In case of chain bolts, it's a simple medicine. But when we go for the staggered bolt, our gauge length and our pitch will be coming into the picture, right? So in this case, our net area is given by first B minus ND. Same way, B minus number of bolts into diameter ND. So in this case, how we are calculating? Uh, we will have different sections. So like if we have this section, 1, 2, 3, 4. If we have 1, 2, 3, 4 section, our net area will be different. If we have this section, our net area will be different. Or if we are considering this section, like this section, our net area will be different. So it will depend on at what point you are calculating your net area. So this is the width and uh, B minus ND plus effect of our uh, due to uh, due to our staggered bolts, there will be the effect. So the net area will be increased by this value PSI divided by 4GI. So this will be there. So our net area will be increased by this value multiplied by thickness same. So this is in case of our staggered bolts. Okay. This is the first case where second case is in case our bolts are in different kind of lines, like our gauge length is not constant or our pitch length is not constant. If we have different type of gauges and pitch, in that case, our net area is given by B minus MD plus whatever the pitch of first bolt divided by gauge of that bolt plus the pitch of second bolt divided by gauge of that bolt. So it will depend on the position of our bolts. Okay, this is what you might have studied in this fourth week. If you guys have any doubt, you can ask me now. Then we will go to the different questions. If there is no doubt, then we will go to the question and answer session for today. First question is eccentric connection subjected to both shear and tension should be checked against combined shear and tension using which form? Anil's formula, interaction formula, Euler's formula, or all of them? We have seen in our first slide itself. This is our interaction formula, VSB divided by V of, shear strength divided by design shear strength square plus tensile strength divided by design tensile strength square should be less than equal to 1. Next question. For eccentric connections, when load is lying perpendicular to the plane of bolted joints, the line of rotation or the neutral axis is assumed to lie at what height? Measure from the bottom edge of bracket to the center line of the topmost bolt. 1/3 of the depth of bracket, 1/5, 1/7, or none of the above. See, correct? So we have seen that diagram, right? Where we have different bolts, and then we have this stress diagram, and we were saying this was our stress diagram, and this neutral axis was at the height of h by 7 from the bottom. This is 1/7 of the depth of bracket. Next question. In case of staggered bolts, the net cross-sectional area along the chain of bolt is increased by increase in staggered pitch, decrease in gauge distance, increase in thickness of plate, or all of the above. So this is the formula which we are using. Normally, we are telling our cross-sectional is given by B into thickness, right? And B is decreased due to our bolt holes. But this effective area is increased due to this formula, is increased by this formula. If we see from these all option, what do you think is the correct option? Checking from this formula. You can see from here, first thing is P into T, P square into T divided by 4GI, right? So P is our pitch length. So if we are increasing our pitch, our strength will increase. Oh, sorry, cross-sectional area will increase. So first option will be correct. Second is gauge length. So decreasing gauge length, our sectional area will increase. So second option is also correct. Third is thickness of plate. So thickness of plate is also directly proportional. So if we are increasing our thickness of plate, our cross-sectional area will increase. So the correct option will be all of the above. Right? Next question is the tension and shear force in each bolt of the joint as shown below respectively are. So this is our bolted connection given and our load applied is 250 kilonewton. So we have to calculate tensile and shear forces. I will give you 2 minutes. You try to calculate, then we'll solve the sum. So what is given to us? A PU value is given to us as 250 kilonewton, right? So since this is not acting at a right angle and these values are given here. So we can calculate this is PU. We can calculate PX and PY, right? This is our theta angle. So Px will be given by cos theta and Py will be given by sin theta. if this is a theta angle, then base is 4, hypotenuse is 5. We can calculate Px, and Py we can calculate same way. Okay. Next is the, we will calculate tensile force. So tensile force is given by 4 Pu divided by 5 into 6. How this value is coming? You ready? It is Px divided by 6, because there are 6 number of bolts. So if we see this thing, this force is going in one direction, and this will be a tensile force, and this will be a shear force, right? In this direction it will be tensile force, and in this direction it will be shear force. It is clear, na? Because in direction axial tensile will be there, and shear force will be in the perpendicular direction to the force, right? So if we calculate this thing, this Px will give us the tensile force. Now what is asked us to calculate the forces each bolt. So we will divide it by the number of bolts. That will give us the tensile force, which is telling us 33.53 kilonewtons. Same way, if we calculate shear force in each bolt, it will give us by P by divided by 6 will be our shear force. Is this question clear to everyone? So next question is, a 12 and thick bracket is connected to the flange of a column by using groove weld. Calculate the horizontal shear stress due to bending. So our P value is given by 60, E is 200 mm, D value is given by 300 mm. We have to calculate the horizontal shear stress. First thing is, as we have seen in design of weld, first thing we will calculate is the throat thickness. So throat thickness is will be given by, if you imagine from this point of view, this will be the type of weld, right? And this butt weld is there, means this is fully filled by the welding, and it will depend on the thickness of our plate. The complete thickness of plate will give us the complete thickness of our welding. So effective throat thickness will be thickness of bracket given by 12 L. So what we have to calculate? We have to calculate shear stress due to bending. It is given by, in case of butt weld, it is given by 6M divided by Te into D square. Right? So moment will be P into E. Throat thickness we have calculated as 12, and D is given to us as 300. So we can calculate the shear stress. Really? So shear stress is coming as 66.67 gigapascal.
Ma'am, here we calculate like in Q is equal to P by
Uh,
2D.
yeah, it's shear stress due to bending. So that's why we are taking the
Oh.
bending formula.
Okay.
Next question is, calculate the net area of the angle ISA 80 into 80 by 6 that is connected to the gusset plate through a single leg as shown in the figure. Bolts used are 4.6 grade and having the bolt diameter equal to 18 mm. I think we have not seen the design of net area, so we will do it by using this question only. So first thing, what is given to us? Bolt diameter 18 mm. So from bolt diameter, we can get the clearance. It depend from this table, we can see the clearance. Mostly we are taking 2 mm as clearance, and this will give us the hole diameter of bolt hole will be given as bolt diameter plus standard clearance 20 mm. So how we will calculate the net area? So we have L section. So the net area of this section will be a total 80 minus 6 by 2. 6 is this thickness. 6 by 2 into 6. And area of the connected leg. This leg, area of this leg, how we are calculating? 80, total 80 minus 6 by 2, 6 by 2 minus this bolt diameter, bolt hole diameter multiplied by thickness. Okay, we can calculate area of this leg as well as this leg, and summation of these two area will give us the total area of the plate. Sorry, total area of the angle section. Is this question clear? Next question is, a double V groove weld is designed to carry an eccentric load of 80 kilonewton. Calculate the depth of weld required. So in this case, we have to calculate the T value. What is a double V groove weld? It's a butt weld. So we will follow the design of our butt weld. What is given to us? First, we'll calculate the throat thickness. Same way, throat thickness will be same as the thickness of our plate, 12 mm. Then we will calculate our weld strength. Weld strength is given by Fy upon gamma m. Fy in this case, Fy space is 250. This is for the weld. This is not for the steel. So for weld, Fy is given by 250 kilonewton. And next thing is we have to calculate the depth of weld. So this formula we have seen. Depth of weld is given by under root 6 PE TE into RW. So P is given, E is given, throat thickness we have calculated, RW we are calculating from here, and this will give us the depth of weld, right?
Ma'am, small thing.
Hmm.
Why we are considering thickness of throat thickness equal to size of thickness of plate?
Just imagine from this point of view if you are seeing it.
Hmm.
So this is our thickness, plate is this much thick, right? And this will be completely filled by our felt part.
So we are not considering like previously we considered like 5/8 of the thing or 7/8 of the thing.
Like in the normal well design. No, 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 no.
Huh.
Here
Okay.
we are considering as the complete thickness of plate only in case of
Okay.
eccentric.
Okay. Got it.
Next question is, calculate the minimum net area for the plate shown below connected to 16 mm thick gusset plate with 20 mm diameter. So we have bolt in a staggered way, and we have to calculate the minimum net area. So what we will do, we will divide our plate section into different sections, and we will calculate different areas, and out of that we will calculate the minimum area. The minimum area will give us the minimum net area. So what is given to us? This thickness of plate is given to us. How we are calculating net area? Thickness minus ND into thickness of our plate. Plate thickness is given as 14 mm, and diameter of bolt is 20 mm. So what we are doing, same way we are taking standard clearance as 2 mm, and the diameter of bolt hole is given to us as 22 mm, 20 plus 22, and we will calculate it for the different parts. So what we are doing first is we are calculating at this section 111. At 111, what we are doing? 170 minus 3 into hole diameter into thickness of plate. Second is 1, 2, 2, 1. This area. Okay. For this area, we have 4 bolts, right? And last is the 1, 2, 3, 2, 1. In this area, we have 5 bolts. So, and but this thing will increase. This is the what we say bolt. Last we have seen where so this extra area we have seen in plastic. Then I forgot the exact name. Some bolt width or something like that. Bolt side. I forgot it. Okay. So in this second part, first part is simple. We are calculating, and second part, what we are doing? E minus these thing plus effective area we are taking due to pitch. Sorry, this is due to pitch. In this case, our pitch is 30 mm. So, what was the formula? 2p square divided by 2p square divided by g. It's not this. Ah, this one. P square divided by 4gi. So this we will use this formula in this case. P square divided by 4gi. So in this case, why we are taking 2? Because this 30 in and 30. 2p will be coming. So p square divided by 4 into g. Gauge distance is given as 25 mm. Okay. And in case of last part, this one, what we are taking, this p, 1p, then second p, then when we are coming from 3 to 2, third p, and then coming to 2 to 1, 4p. So that's where we are multiplying by 4. 4p square divided by uh, p square divided by 4g. So using this formula, we are calculating 3 area, right? Out of these 3 area, which is the minimum area? So minimum area is given by 1344 mm square. Okay. Is this question clear? So next question is, an increase in the ductility of the tension member will have no effect on the strength of tension member, decrease the strength of tension member, increase the strength of tension member, or may increase or decrease the strength of tension member. We have seen in our slides previously. If we are increasing the ductility, it will increase the strength of tension member. Okay. Next is the flip angle connection are designed to transfer small end movements in addition to the large end shear, transfer large end shear only, transfer small end movements only, or transfer bending. So first we will see what exactly are the clip angles. So if this plate is connected to the this plate, so we are using bolt here. in addition to these bolts, we are actually providing one extra angle section at the back side, which will give us the which will provide the extra support to our section. So these type of clip section are actually help to transfer the small end movements in addition to large and shear. Okay. So this is the definition of clip angles. You can read it afterwards. Next question is, in the figure shown below, find the size of wind. What is given to us? Shear stress is given as 247.52 divided by size of wind, and FP is given as 1039.6 divided by size of wind, and RW is given by 189.37. Can we calculate the size of wind? Sorry. We can directly use our simple formula of resultant stress, which is given by, say, because in this case, nothing is given. Nothing is given. So we are assuming that it is our fillet weld. So in case of fillet weld, what is given as resultant stress is Q square plus FB square under root. So Q is given to us, FB is given to us. We can calculate the resultant stress FB, and we know that our FB should be less than RW. So less than equal to, let us equate it. So FB is equal to RW. From here, S we can get as 5.64. Why? So approximate S will be 6 mm. Why we are taking more? More the S value, less will be our complete value. So our FB should be less than equal to RW. So therefore, S we will approximate S to the larger value. Okay. So that's all for today's session. If you guys have any doubt, you can ask me.
Yeah, in this particular question, I think even 8 is also correct. I guess the 6 is like more economical way, but it
8 is,
is should.
yeah, 8 can also be there. Option is there, 8 of 8 is there an option. But the approximate value which we are getting is 5.667. So
Hmm.
I think based on that, we are taking 6 mm.
Ah,
If it's a numerical question, you can write 8 mm if you have to do complete design. But if
hmm,
it's a MCQ question, you will always try to get the nearby value, right?
hmm. Yes. And also, ma'am, can you clear? I mean, in a problem in the video, in the sir lecture, I got to confuse again with respect to these basic things like pitch and edge and gauge distances. So, can you just in a picture, can you draw and clarify these things?
In the normal, you are telling
Yes, in a normal in bolt connection
bolt
plates.
connection.
Uh,
So, can you see this page?
yes, ma'am, I can.
So, one plate is in this. There are two plates overlapping each other, and we are connecting them through the bolts. So, if load is applied in this direction, the distance between two bolts in the direction of load is given to us as pitch distance. And the distance between two bolts in the direction perpendicular to our force is given as gauge distance. Okay. And same way, in the direction of force, the distance between last bolt and the plate end is given as end distance, and the distance between the last bolt and the plate end in the perpendicular direction is given as edge distance. It easy to understand?
Yes, only. So the pitch and end are in same line, and the
Yeah,
gauge and edge are in the
edge are
same line.
same. It depends on
Yep.
your line of force. If,
Hmm.
in the line of force, it's pitch. Perpendicular is gauge.
Okay.
There are no doubts. Then we'll close the class for today.
Yes, ma'am. Can but small request, ma'am. Can you upload this PPT a little sooner so it will be helpful for the assignment?
I uploaded the PPT last time, no?
Yes, ma'am. I mean,
Okay,
if you
you mean today itself?
sooner, little sooner, yes,
Okay,
ma'am. Today or tomorrow, anything, yes, ma'am.
okay, I will upload.
Yes, ma'am. Thank you.
Thank you.